This is James with a gentle introduction to Bayesian networks, which can be used to model real-world problems. In this video, we're going to look at two problems that can be modelled using Bayesian networks. The first is known as the Harvard Medical School problem, and the second is the case of a chest clinic where a patient's condition is being diagnosed. And where we are heading with this in a future video is risk analysis of IT systems. Let's start with the Harvard Medical School problem. Because it's such an interesting problem, we will look at it from three different perspectives: graphically or intuitively, mathematically using Bayes' theorem, and finally using a simple Bayesian network, which is based on Bayes' theorem. So the problem goes like this. You've just tested positive for a rare disease. You are told the test is 100% reliable if you have the disease, 95% reliable if you don't have the disease, there's a 5% chance of a false positive, and the disease occurs in 0.1% of the population. What is the chance you have the disease? The most common answer at the Harvard Medical School was 95% chance, but the real answer is a surprising 2%. How can this be? Firstly, let's look at the problem graphically. On average, the disease occurs in 0.1% of the population. So in any random group of 1,000 people, it's expected that one will be sick and will test positive. The red dot indicates that one person who is sick, whereas the other 999 are not. There is a 5% false alarm rate, so 5 out of every 100 people will return a false positive test. The dark grey circles indicate the false positives. This equates to 50 false positives for every 1,000 people tested, and a total of 51 positive tests overall. If you pick one person at random from the 51 who have tested positive, only one is actually sick. So there is a 1 in 51 chance of being sick if you are tested positive, which equates to approximately 2%, which is quite a surprising result. So let's confirm that another way. Let's look at it mathematically using Bayes' theorem. The theorem uses this notation: the probability of being sick given a positive test. In other words, the probability of a hypothesis given an event, where the hypothesis is being sick and the event is a positive test, also written as the probability of H given E. And here is Bayes' theorem in its general form. Describing it using our sick and positive test case, it goes like this. The probability of being sick given a positive test is the probability of a positive test given you are sick times the probability that you are sick divided by the probability of a positive test. Now we take this equation and expand the bottom term to give the equation at the top. The term on the bottom is the probability of a positive test if you are sick plus the probability of a positive test if you are not sick. Now, substituting some values, we have 1, the probability of testing positive given you are sick. It's 1 because the test is 100% accurate if you are sick, times the next term, 0.01, the probability that you are sick, which is 0.1% of the population on average. The top term is the same as the first half of the bottom term. Then we have 0.05, the probability of testing positive if you are not sick, which is 5%, the false alarm rate, times 0.99, the probability that you are not sick, which is 99.9% of the population on average. So simplifying this, we have these numbers, and simplifying further, we have approximately 1 over 50, which is about 2%. So this is convenient. The graphical solution is backed up by the maths. Now we move on to another way of solving the problem. Here we model the problem using Netica, an application for building and running Bayesian networks. The model is a simple two-node network. The first node is the disease node, which has two possible states, sick and not sick. The second node is the test node, which has two possible states, negative and positive. It starts off with no evidence, and so the probability, on average, of not being sick is almost 100%. The probability of a negative test is about 95%, and the chance of testing positive is a little over 5%. Now let's enter some evidence. If I'm sick, I click on the sick element of the disease node. I'm definitely sick and have a 100% chance of testing positive, because we know the test is 100% reliable when testing sick people. Now I click on not sick. If I'm not sick, I have a 95% chance of testing negative and a 5% chance of a false positive. Now here's where it gets very interesting. Not only can we do forward reasoning from cause to effect, from disease to symptom, we can also do backwards reasoning from symptom to disease, from effect to cause. I reset the network back to its original state of no evidence. A new person has walked into the clinic and we test them. They return a positive result. On the test node, I click on the positive element to indicate a positive test. And now we see the probabilities of having the disease have been recalculated. And the probability of being sick is about 2%, consistent with the two earlier calculations. How did this work? Well, it's been calculated for us by the network, but it depends upon us entering the correct values in the conditional probability table. If I view the table for the test node, it looks like this. If I'm sick, I have a 100% chance of testing positive. If I'm not sick, I have a 95% chance of testing negative and a 5% chance of testing positive, the false alarm rate. So this is helpful in a two-node scenario like this, as it means I don't need to do the calculations myself, but it's also graphical and can be easily added to. Next, we're going to look at the chest clinic. This is a model of a chest clinic where we want to diagnose a patient. The nodes at the top are possible causes of a disease. In the middle are the diseases, and at the bottom are the expected symptoms. The smoking node is connected to the lung cancer and bronchitis nodes, indicating that being a smoker means you are more likely to have lung cancer or bronchitis than a non-smoker. And if you have any of these conditions, TB, cancer or bronchitis, you are more likely to have dyspnea, which is shortness of breath. The network is in the no evidence state. You know nothing about a patient who has just walked into the clinic. They have a 50-50 chance of being a smoker or a non-smoker. It's not saying 50% of people are smokers, but 50% of people who come into the chest clinic are. So let's enter some evidence. We find out the person is a non-smoker. We click on the non-smoker element of the smoking node. The probability of lung cancer went down, along with the other probabilities. The most likely disease at this point is bronchitis. You then find out they suffer from shortness of breath. You click on the present element of the dyspnea node. The chance of bronchitis will go up. It's gone up from 30% to 75%. The patient then goes off for an X-ray and comes back positive. Clicking on the abnormal element of the X-ray result node, TB and lung cancer go up, but they are still less than bronchitis. However, now we find out they've been travelling overseas recently. Click on the visit element of the world travel node. The chance of TB goes up and is now the most likely explanation of the symptoms. So this model shows how a relatively complicated case of patient diagnosis can be modelled using a Bayesian network. So there we have it. We've demonstrated how Bayesian networks may be applied to problems like the Harvard Medical School problem, which we solved not only using a Bayesian network but also graphically or intuitively as well as mathematically. And we also looked at a more complex example of a chest clinic where we wanted to diagnose what condition a patient might be suffering from. Thank you for watching. Finally, I'd like to acknowledge the following sources that I drew on for this video. 3 excellent YouTube clips from the Veritasium channel from Norman Fenton and the University of New South Wales. There's an excellent book on risk assessment and decision analysis with Bayesian networks by Fenton and Neal. And also here's the link to the Netica software from Norsus. Thanks again for watching.